And I'm going to share the screen. Then I have a correction to make on the correction that I shouldn't have made yesterday. I don't know why, I just kind of spaced out on it. So I think I had, oh, over here. I think I had, during the class, changed this to NNN, triethyl. But I didn't remember that, you know, the first ethane is right here, right? So I forgot which methodology we were using. So you don't have to change anything. What I was talking about was wrong. I was spacing out there. Again, what I'm talking about is that this right here is the root name. And then you have substitutions on the end. So with this one of these is the longest continuous chain with the nitrogen. And two of those are substituents. Okay, let me check this email here. Okay, hold on a second. I gotta do a chore. What the heck is going on here? Sorry, having some issues with this other site. Announcements. Okay, sorry about that. So, going back down to where we left off, so I gave you a lot of information about drugs. I'm not promoting drugs, just FYI. Okay, so now aldehydes and ketones. These are usually put together because of their similarities. They both have what's called the carbonyl group. So the carbonyl, or called the oxo group, or the keto group, is the carbon to oxygen with a double bond. Okay. So aldehydes have a hydrogen on on that carbon right there. So this is the smallest aldehyde you can get. Here's the next smallest aldehyde you can get. So the aldehyde has the carbonyl group, and there's a hydrogen bonded to that carbon. So keep in mind that this carbon to hydrogen bond is nonpolar, even though the carbon to oxygen bond is polar. So the root is the longest carbon chain containing the carbonyl group. You make it end in Al for aldehyde. Then the carbonyl group is always going to be carbon number 1. So we don't have to put it in the name. Then you just number the substituents. So one carbon in a row, methane would become methanal. Common name is formaldehyde, quite the toxic substance. Then ethane becomes ethanal. Common name is acetaldehyde. This is what gives you the hangover after drinking ethanol. Because if you recall, ethanol being a primary alcohol, if you oxidize it one step, you get the aldehyde. Let's see. So here in the stick figure things, I got 1, 2, 3, 4, 5, 6 carbons in a row. So hexane becomes and al, and we don't need to put the number 1 because that takes the priority. We're naming it as an aldehyde, so that carbonyl carbon gets number 1. So on the number 2 position, there's a methyl group. So 2-methyl hexanal. Now we need to remember this one. If I take the carbaldehyde group and I put it onto a benzene ring, it's called benzaldehyde. And this actually gives you the flavor of bitter almond, benzaldehyde. So if you look at some substituted benzaldehydes, here's benzaldehyde right there. Okay, so you have a hydroxy here. That would have been a hydroxy here, but they put a methyl group on it. So in terms of numbering system, it's going to be 1, 2, 3. So 3, 4 would be the lowest numbering system. And then we have methoxy, and then 4-hydroxy benzaldehyde. And this is the flavor of vanilla. Okay. And here's another one. So look at the name of this one, propenal. What does that mean? So 1, 2, 3, it would be propane. It's propanal because it's an aldehyde. But what about that double bond right there? So we just put it as propene. And then you could have put prop-2-pene al as well. It's okay to do that. So that's where the double bond is, carbon number 1, carbon number 2. And then on carbon number 3 is a phenyl group. So benzene, when it's attached as a substituent, is called phenyl. And then this right here has the possibility of being cis or trans. So the big one's here, the big one's opposite, so it's trans. So this is the flavor of cinnamon. So notice that the name of this compound, the predominant functional group on here, in other words, the most oxidized carbon, is the aldehyde. So we name it as an aldehyde. We're not naming it as a benzene. We're not naming it as an alkene. We're naming it as an aldehyde. Okay. If you have some big, giant, complex molecule somehow, and you have the aldehyde functional group put on there, it's called carbaldehyde. So some big molecule named Fred would be called Fred carbaldehyde. This would be cyclohexane with a carbaldehyde group on it. Okay. An alternative naming system would be methanal, and then put cyclohexyl on there. That would have been okay as well. So questions so far? Sorry, I have to keep checking my email here. So what is a ketone? The ketone also has the carbonyl group, but it's bonded to 2 carbons. The carbonyl carbon is bonded to 2 carbons. So root is the longest carbon chain containing the carbonyl group. The name ends in ONE because of ketone. And the carbonyl group gets the lowest possible number. So in an aldehyde, the carbonyl group is always number 1, but not in a ketone. You have to tell it what the name is for the most part. So this one right here, 1, 2, 3 in a row, and it's a ketone. So it would be called propanone. Why do we not need the number 2 in the name? What would happen if you tried to say 1 propanone? 1 propanone would not be a ketone. It would be an aldehyde. If I move the carbonyl group to a terminal carbon, either side, it becomes an aldehyde. So the common name for this is acetone. So what about this one? I got 1, 2, 3, 4, 5, 6 in a row. So it's going to be hexanone. And where is the carbonyl group? 1, 2, 3, or 1, 2, 3, 4. So 3 hexanone, that sets the numbering system. So this is 4. So 4 methyl, 3 hexanone. So 1, 2, 3, 4, 5, 6. It's hexanone again. It's 2 hexanone. So that sets the numbering system. 3, 4. So that's 4 methyl, 2 hexanone. So notice that I often choose structures that indicate certain things to you. Then 1, 2, 3, 4. This should be 2-butanone. So why do they not put the number 2 there? Well, we don't need to. If I put it here, it's on the 2 position. If I move it over here, it's also on the 2 position. And the common name for this is methyl ethyl ketone, often abbreviated MEK. That's a common solvent. You can buy that at many hardware stores. They use it for mastics, for putting down floor tiles and stuff like that. Well, it's a solvent for the mastics, I should say. So here is an interesting one. This is cyclohexanone. So we call it cyclohexane, but it's a ketone, right? So cyclohexanone. So that'd be carbon number 1, 2, and 3. So on the 3 position, there's a methyl group. So 3-methyl cyclohexanone. So notice this one, I'm naming it as a ketone. So the benzene just simply becomes a phenyl group, a substituent. So 1, 2, 3 carbons in a row, so propanone. And notice that I don't need to say 2-propanone. If you did that on a test or something, I'm not going to like call Homeland Security or anything. Not a big deal. And also on the position, number 1 position would be the phenyl group. If I would have put the phenyl group over here, it would still be 1 phenyl. So we don't need to put the number 1 there. So notice this one, I got 2 in a row, so the benzene ring just becomes a substituent. So ethanone, and on the 2 position, there's a phenyl. So 1, 2, oh yeah, 1, 2. That's the 2 carbon right there. So in effect, do we really need the 2 right there? The answer is no. So a couple of years ago, I had free access to this computer program. That's where I got a lot of these structures from. And I didn't buy the computer program. It was very expensive. And there was just a lot of mistakes. And you couldn't control it very well. And so I didn't buy it. But, you know, kind of points out that there's inconsistencies all throughout the literature, all throughout everything, which is why I just get, for the point of this course, as long as you give me a name that describes one particular structure and nothing else, that's what I'm looking for. And occasionally we have diones. Okay? So we have 1, 2, 3, 4 in a row. So butane dione or butadione. And another common name for this is biacetyl or diacetyl. So bi and di mean 2, right? So here's one acetyl group, here's the other. And so that's the aroma of melted butter. That's artificial butter flavor. So some physical properties of aldehydes and ketones. The carbonyl group is polar. The aldehyde carbon hydrogen is not. Aldehydes and ketones cannot hydrogen bond with themselves, but they have dipolar attractions. So if you were to compare an aldehyde or a ketone to an alcohol, alcohols can hydrogen bond to themselves. Aldehydes and ketones cannot. Only dipole-dipole attractions, which might explain to you why you know acetone, that's fingernail polish remover. It's a liquid and it evaporates very quickly because it has rather weak attractive forces. So I think I'm going to, sorry, checking my email again. I'm going to draw a few attractive forces on the iPad here. So say we have something like acetone. Okay. So here's the complete Lewis structure for acetone. So I see that this is the polar bond right here between the carbon and the oxygen. So this would be the partial negative, and that would be the partial positive. But this other non-binding electron pair can also act as a partial negative. So this partial positive is going to attract the partial negative of another acetone molecule. Well, what would that be? The non-binding electron pair on the oxygen. So what kind of attraction is that? Well, it has London because all molecules have Londons. There's a dipole and a dipole. It doesn't meet the criteria for the hydrogen bond. The answer is no, because there is no OH. There is no fun in both molecules. What about with water? Okay, well, with water, this partial negative right here would attract the partial positive of a water molecule. That would be the hydrogen. Is that a hydrogen bond? So here's the OH of one. What do I need in the other one? An F, an O, or an N, and there's the O. What about this partial negative over here? That would attract also the partial positive of a water molecule. Another hydrogen bond. What about this partial positive over here? That would attract the partial negative, right? But of a water molecule, that's going to be the oxygen. Now, what kind of an attraction is this between that partial negative and that partial positive? Here's the O. Does the other molecule have an FH, an OH, or an NH? The answer is no. So in other words, we get only two hydrogen bonds possible between water molecules, and no hydrogen bonds possible between ketones. And if instead we were looking at, say, an aldehyde, when I go to put the partial charges on here, so here would be the partial positive, here's the partial negative, and I could put one over here as well. But there is no charge here. That's a non-polar covalent bond. So any questions on that? Okay. So we get to the chemical properties of aldehydes and ketones. And I didn't really put this in a red box. I put it in a black box because I want you to know this, but because it will come up in another course. And I don't want to feel like I didn't prepare you for another course. But here's what ketones and aldehydes can do. So I don't have a way to put the mechanism because I don't really care about mechanisms right this second. But anyway, as it turns out, in the old-fashioned nomenclature, this center carbon, the carbonyl carbon, did not get any designation before they started using numbers. If you go out one, that's an alpha carbon. If you go out one this way, that's also an alpha carbon. If you go out the next one, that's a beta carbon. So it turns out that because of the electron withdrawing capabilities of oxygen, oxygen is pulling that way. This means it's pulling that way. And I'm pulling electrons away from one of those hydrogens slightly. And this already has a partial negative charge. So there's an attraction between that alpha hydrogen and that oxygen. So in the occasion, if one of these hydrogens does jump on here, you form an alcohol group. And then now that carbon is looking for another bond. So it forms a double bond with this carbon, and we give up that double bond here. And what you get is an enol. Here's the ene, and here's the ol. So if you're doing a synthesis reaction in a test tube where you don't have a catalyst such as an enzyme to direct how the reaction goes, oftentimes you will get products formed not from the keto form, but from the enol form. It's just another example of why when you do test tube synthesis, you're not going to get a single product. But with an enzyme-directed reaction, you get a single product. Because the enzyme is going to bind this substrate right here and either hold it into the keto form or make it transform into the enol form. That's part of the transition state. But we're not going to use that in this course because we're not really doing mechanisms. So the first thing we'll look at is the oxidation of aldehydes and ketones. So an aldehyde can be oxidized to a carboxylic acid, but a ketone cannot be oxidized. So you might be wondering why. One explanation would be because that's God's will. Another explanation would be is that here's a carbon and a carbon. So those electrons are shared fairly equally right there because the difference electronegativity, which is one indicator, would be 0. So those electrons are fairly happy. But over here, there is a difference in electronegativity. It's not great, but it's enough for oxygen to come in there and insert itself between that carbon and oxygen atoms. So oftentimes in the lab, you're trying to figure out, well, okay, I see the carbonyl group, usually from infrared spectroscopy, but is it an aldehyde or a ketone? Well, then we do either the Tollens, Benedict's, or Feelings test. So I just thought I would just show this to you because it's kind of interesting. So in the Tollens test, you put silver in there, and the silver, if it can oxidize the aldehyde, this is the oxidizing agent. So it itself gets reduced by the electron, and you form this silver mirror inside the test tube. And it's really quite pretty. It's like a real silver mirror. And I used to have students all the time, oh, can we have this? Can we take this home? I go, yep. Is it really silver? Yep. And the Benedict's and Feelings reagents use the copper ion. So when the copper ion gets reduced, well, when it's not reduced, I should say, it forms in water these beautiful blue complexes. So they're called coordination bonds between water and the copper. And it's this really beautiful translucent blue. It's just what makes somebody want to go into chemistry just so they can make those kind of solutions. But if the aldehyde gets oxidized, then the copper ion gets reduced, and then you form this red precipitate. And then aldehydes and ketones can be reduced. So here is XH2. What does XH2 want to do? Turn into X. So it needs to give its hydrogens to somewhere. It's going to give it to the functional group because, carbons are, hydrocarbons are inactive. So yeah, one carbon goes there. One hydrogen goes there, another one goes there. So essentially, you're saturating that double bond with hydrogen atoms. So if you do an aldehyde, you end up with a primary alcohol. If you do it to a ketone, you end up with a secondary alcohol. So we've seen some condensation reactions before. And I remember as an undergraduate being confused. To me, a condensation reaction is, oh, you see water condensing somewhere. But in organic chemistry, it means that two organic molecules are condensing, are becoming one. So we saw that before, for example, when two alcohols were oxidized and you formed an ether, or when two thiols were oxidized and you formed a disulfide. Those were also condensations. So aldehydes and ketones will form condensation reactions with alcohols. So you form a hemiacetal, and then an acetyl, or a hemiketal and a ketyl. And I'll try to explain what that means as we go along. So again, you see this reaction on exam 2. Your job would be to draw this product over here, right? How would you know? We could memorize it, but that doesn't really help you all the time. So doing chemical reactions is a combination of memory and a combination of looking for cues that help you figure out what's going to happen. So the way I teach organic chemistry, I use electronegativity to find out where this partial charge is. And this is what you will always know. A partial negative charge will always attack a partial positive charge. A partial negative charge is never going to attack something that's negatively charged, right? And when you do organic mechanisms, it's all based upon Lewis acid-base theory. So instead of having in Bronsted-Lowry base theory, it's the hydrogen doing the attacking. In Lewis acid-base theory, it's always the electron pairs doing the attacking. And the electron pairs are always going to attack something that's partial positive. So here's a way to think about this. And again, I'm not going to ask you for the mechanism. I'm drawing this arrow right here to help you draw the product. So looking at the alcohol, here's the partial positive on the hydrogen, here's the partial negative on the oxygen. Looking at the carbonyl group, here's the partial positive, here's the partial negative. So if I draw this arrow, that becomes the new bond. Okay. So then I have to put a bond between this carbon and that oxygen. That's really that bond right there. So I probably should color that somehow. So we're forming that bond. Okay, well, that means that now this carbon would have 5 bonds. So it has to give up this one over here. So these pi electrons jump up on this oxygen atom, and that would give that a full negative charge right there. This then would have a full positive charge, so this hydrogen ends up over here. Okay, maybe this would help if I did this. Okay. So how do I know if I did it right? If you did it right, you will get what I call an etherol, because that's exactly what it is. Here's an ether, and here's an all. But what the organic chemists like to call it, oh, it's a hemiacetal or hemiacetal. But that doesn't really tell students what they're looking at. It's an etherol. And I'm sure I'm not the first one to make that up. Okay, now I see I did this in blue. Maybe I'll make this in blue. Trying to make this, trying to improve this all the time. It's not the right blue, but that's okay. So now, what if I take this and I bring in a second alcohol? Okay, so here's another condensation reaction. What's going to be happening here? Well, this is an ether, and what we know about ethers is they're very stable. They're not reactive. But what if you know, or remember reaction 13? What happens when 2 alcohols get together? There's a dehydration, and you form an ether. That makes sense? So what is a full acetal? It's really a diether. So here I split it up into 2 different chemical reactions. One gives you the hemi, which is an etherol. The other one gives you the diether. So this is with an aldehyde. Now we'll do it with a ketone. So I see the partial negative from the oxygen is going to attract the partial positive of the carbonyl carbon. That's going to be a new bond that's formed right there. I should put that as red. Of course, this is all mute if you're colorblind. But I found the use of color is extremely valuable. Okay. For those who are not colorblind. So anyway, here's example 2. So this is going to attack there. That's going to make that new bond right there. I have an etherol. Here's that same bond again. Now if I bring in the second alcohol, what's it going to do? It's going to go right there to form my diether. Okay. So what's the difference between an acetal and a ketal? One has a hydrogen here, and the other one has a carbon there. That's the only difference. So what do you do differently if there's an aldehyde versus a ketone? Nothing. Okay. And there's a move right now for people to not use ketal and acetal anymore. They don't really use etherol and diether. That's kind of my invention. So hopefully they'll come around one day. Then the reaction may be shown in one step, going all the way to the full acetal or full ketal. So what would you do? You'd have to know that this starts over here, making that new bond. And then this is going to go over there. So another way to think about that is that you're taking this carbonyl bond right here, which is an unsaturated bond, and you're completely saturating that bond with alcohols. So that is a complex reaction, but hopefully that explanation helps. Check my email here. Okay, sorry. So what about between themselves? This is called the formation of an aldol. So aldol formation. So an aldol is a beta hydroxycarbonyl compound, either an aldehyde or a ketone. And so I put the partial mechanism in here in the red box. Again, I'm not going to bother you with mechanisms unless it helps you get the product. And here's a case where it does do that. So it turns out that alpha hydrogens are slightly acidic. That's in water. But, you know, it's not really going to change the pH or anything because water is such a weak base. But what if I put it in there with a stronger base like hydroxide? Now I can make this acid-base reaction happen more prevalently. So the only acid able to do anything with the hydroxide is the alpha hydrogen right there. So occasionally, well actually not even occasionally, you can actually in a test tube convert all of it into the carbanion form. So this is what's called a carbanion. Okay, that's a full negative charge. So why does the carbanion even form? Well, partially because it's stabilized by resonance. So these are resonance structures. So I'm able to take that -1 charge and spread it across 3 different atoms, or at least 2 different atoms, diminishing the magnitude of that negative charge. Okay. So, but anyway, what does the carbanion do? It's going to attack something that is partial positive, right? Not of itself, but on the other molecule. So here's the other molecule. There's the partial positive right there. So it is going to attack it. It's going to make a new bond. Okay. Maybe this new bond should be red. I don't know. Can't get a hold of that right this second. Anyway, so I form that new bond, and notice this hydrogen just goes there. Now that the carbon just bonds there, it makes that new bond. And what happened to the rest of it? Nothing. It didn't do anything. It just formed that new bond. But what happens to this carbonyl carbon? It can have 5 bonds, so it has to give 1 up. So when it does that, now it has to interact with the solvent because water is weak acid, but this now becomes a very strong alkoxide base. Maybe it's better to call this a base. So I'm going to have to save this anyway. Okay. So then you end up with, oops, that's a good, okay. You end up with a neutral compound. And so why is the hydroxide written over the arrow? Because it is a catalyst. Okay. Notice that when you take the water at the end and you donate the hydrogen ion to it, you regenerate the hydroxide ion. So let's do an example. So I'm looking at this carbon right here. I'm seeing that hydroxy group. That hydroxide ion is the key that tells me that I'm looking for alpha hydrogens to take off. None over here, none over here. Look how hairy. Put those chlorines over there to make sure that there's no hydrogens there. So the only molecule that has hydrogens is this one in the alpha position. So what that means is that the hydroxide is going to take off the hydrogen from this alpha carbon. So that forms the carbanion right there. It's going to attack right there and form that new bond. Does that make sense? So all you have to do is form that new bond. Notice that nothing happens with this, nothing happens with this. The carbonyl group that gets attacked turns into an alcohol, because that's what regenerates this hydroxide. So look at the next one. Again, if this were on the exam, I'm seeing that hydroxide ion, and I'm thinking already, where is an alpha hydrogen I can take off? Okay, here's an alpha hydrogen. Here's an alpha hydrogen. Look what the trick that we did. This is identical to this. So it doesn't matter which one I use to attack the other carbonyl group. This one, no alpha hydrogen, no alpha hydrogen. So the only carbanion I can make is at this particular carbon right here, and that's going to have to attack that carbonyl group. So I form that new bond, right? Nothing happened here, nothing happened here, and that carbonyl group gets turned into an alcohol. So, how do we know if we did it correctly? If we did it correctly, we will get a beta hydroxy ketone or a beta hydroxy aldehyde. This is why I gave you this nomenclature over here. Alpha, beta, gamma, right? So did I do this correctly? This gets no designation. Here's alpha, here's beta. Oh yes, it's beta hydroxy, I did it correct. Here's alpha, here's beta, beta hydroxy, I did it correct. Okay. Anyway, so yeah, some of the condensation reactions are a little bit complex. Life is a little bit complex too, isn't it? Here's another condensation between the carbonyl group with amines. And what you form is called an imine. So an imine, for example, is found in the urea cycle. And anyway, if we look at the reaction right here, again, this is what you would see on the exam. What you should think about is dehydration. Can you make water? That's the important thing. So here's one functional group, here's the other functional group. It's going to involve the functional groups. That's where I get my water molecules from. Now, that carbon needs 2 more bonds, that nitrogen needs 2 more bonds, so we give it to them, and we end up making what's called an imine. So let's see. Here would be another one, right? Here's where I would get my water from. So the nitrogen just forms a double bond with the carbon. What about this one? Here's my oxygen. Where's my 2 hydrogens? Oh, guess what? I can't make water because I don't have 2 hydrogens from the amine. There's no reaction. What about with ammonia itself? Yeah, I can make water and I can form the amine. Now, again, the mechanism for this is known, pretty much proven even. But do you think that you're going to break 2 bonds at a time to make this amine? Absolutely not. The activation energy would be huge to break 2 bonds at once. So what does a reaction mechanism do? It breaks 1 bond at a time, then it does something else, then it does something else. So when you take this big energy barrier and you break it up into smaller steps, then it's much more doable. And that's what's happening over here. You're not breaking that double bond all at once. But in practicality, for us knowing how to just draw the product, yeah, you're breaking that bond and forming the double bond with carbon and the nitrogen. So here's an example. Here's an example of keeping ammonia away from cells because ammonia is toxic. Okay. So ammonia is an interesting molecule because you make it during the digestion of proteins, right? But the free amino group, which was ammonia, is extremely toxic. It's small enough, it passes right into cell membranes through their aqueous protein channels. And then when it gets in there, it's a base. So one thing you might even think about, I don't have it here, I have it in other chapters, but Windex is a dilute solution of ammonia. If you spray that on a mosquito, you'll knock the mosquito right out of the air and kill it. Spray it on a cockroach. It eventually gets into the cells of the cockroach through the little holes in the exoskeleton called spiracles, and it will kill the cockroach. It would kill you also, unless you had the urea cycle. So this is how the ammonia is held using the amino acid arginine. Then when it gets hydrolyzed, in other words, going back the opposite direction, you give off, in this case, urea. So here's where urea comes from, okay? And then you get ornithine, which is another amino acid, but you only find that in the urea cycle. So the chemical reactions that we're going through have applications in metabolism. That's why we're doing it. Okay. If they don't have applications, except for in the test tube, then we're not covering them. So anyway, yeah, that's how I feel oftentimes. Yeah, you guys see Breaking Bad?
Yeah.
I put Breaking Bad there up with Gone with the Wind and The Wizard of Oz and all those most iconic things that define culture. To me, that was just an amazing show. Any questions about this chapter at all? Okay, well, I will close that chapter. Don't worry, I'm not going to run out of chapters for a while. Sorry, let me just check my email one more time. Okay, So the chapter on carboxylic acids. So you've seen carboxylic acids because if you take primary alcohol and you oxidize it one step, you get the aldehyde. If you take the aldehyde and oxidize it, you get the carboxylic acid. And so what we're doing here, it's like here's the basic carboxylic acid, right? So here is formic acid, here's acetic acid, okay? So here's the common name, here's the IUPAC name, here's the Latin or the Greek origin of the common name. And unfortunately in nutrition and food and stuff like that, they often use the old-fashioned common name. So this nomenclature right here means that 1 carbon in a row, no double bonds. 20 carbons in a row, no double bonds. Okay? And what we find in biology is that most carboxylic acids, which would include the fatty acids like these down here, have an even number of carbons. And we'll understand why that is when we get to metabolic pathways. The breakdown of fatty acids, you end up getting basically acetic acid, not in the form of acetic acid, but 2 carbons in a row. And when you synthesize it, you start with 2 carbons in a row. So formic acid or methanoic acid, ethanoic acid, propanoic acid, butanoic acid, and decanoic acid. So you should know those. Then we have more I can't even pronounce it. Maybe that's why we don't have them. Okay. So then some of these you've seen in your foods, right? And these are saturated fatty acids. This is no double bonds. Arachidonic acid will come up several times because that's a precursor for the synthesis of several other things. So when we name carboxylic acid, the root is the longest continuous chain that includes the functional group. Drop the E, make it indenoic acid. And the carbonyl group is always carbon number 1, so we don't have to give it a number. Matter of fact, the carboxylic acid functional group really is king of the functional groups. That's the most oxidized form of carbon possible until you get to things like carbon dioxide. So you should really know the name of formic acid and acetic acid, you know, because those are just in common usage. So oftentimes they leave out the hydrogen there on aldehydes. And of course, this would make it an aldehyde, but why do we name it as a carboxylic acid? Because that's king of the functional groups, that's why. So ethanoic acid or acetic acid, propanoic acid or acetic acid, and notice I don't have to say 1 propanoic acid. Then I got 1, 2, 3, 4, 5, 6, 7. So heptanoic acid would be all of this. That's carbon number 1, 2, 3, 4. So on the 4 position, I have 2 methyls. So it's dimethyl and 4,4. Then in this unit, you will have to know benzoic acid. Okay. So if the hydroxy group there were a hydrogen, that would be benzaldehyde. But when it's a full carboxyl group, that's called benzoic acid. So then we could have named this phenol, but alcohols are subservient to the carboxylic acid, so we name it as benzoic acid instead of phenol. And on the 3 position, there's a hydroxy group, or you could call it the meta position if you wanted. So again, here's benzoic acid. In the number 1, 2, 3, 4 position, there's an amino group. So this structure right here could also be called para-amino. So para-aminobenzoic acid, or PABA, is what was used, or maybe still is used, in sunblock. So this system of conjugation right here allows those pi electrons to be delocalized and therefore absorb ultraviolet light. That's why it acts as a sunblock. And then we often have dicarboxylic acids, which we call dioic acids. So here I got 1, 2 carbons in a row. So it becomes ethane dioic acid. Its common name is oxalic acid. And so when I'm doing general chemistry, I always have the students memorize oxalate ion, which comes from oxalic acid, because calcium oxalates often will precipitate in your body and form kidney stones and other things like that. And the oxalates are prevalent in foods that contain taro. What's another one is star fruit, and a couple other fruits that we eat occasionally in Hawaii. So here's 1, 2, 3, 4. So this would be called butane dioic acid. Its common name is succinic acid. So here's benzoic acid, but we could call it 4-carboxy benzoic acid, or we could say 1,4-benzene dioic acid. And the common names end in ic acid. So here we got 1, 2, 3 carbons in a row. So it's propanoic acid, but it's also a ketone, isn't it? So how do we name that? Oftentimes it's the oxo group. We name this as the oxo group. So on carbon number 1, 2, there's an oxo group there. But again, I'm not going to ask you to name compounds with several functional groups. The reason why I put this here, because this is pyruvic acid, also known as pyruvate when it's deprotonated, right? That is the end product of glycolysis, pyruvate. Here's sodium 2-oxopropanoate, or sodium pyruvate. So here is 1, 2, 3, 4. So butanoic acid. Its common name was butyric acid. Notice oic versus ic, right? That is found in sweat. That is found in rancid butter. Not a pleasant smell. And then this one, 1, 2, 3, 4, 5 in a row. So pentane dioic acid would cover all of this. In the 1, 2, 3 position, there's a hydroxy group. And this is called the carboxy group. Okay. So if this were an aldehyde, it would be called 3-carbaldehyde, but because it's a carboxylic acid group, it's called 3-carboxy. Here's another way to name that. And this common name is citric acid. So the citric acid cycle is also known as the tricarboxylic acid cycle because of 1, 2, 3 carboxylic acids on citric acid.
Why is the carboxy group not carboxyl? Or what would carboxyl be with the L at the end?
Sometimes they use carboxyl.
Okay.
Yep, sometimes they do. But it's kind of like when, people write things in English, right? They use their words differently. And yeah, we don't follow exact conventions all the time. So the common names use Greek letters instead of numbers. So the carbonyl carbon is skipped, it's not given a letter. So here's alpha, beta, gamma, delta, epsilon. And you can keep going through the Greek alphabet, which I don't care about knowing. You get to the very end. That's called the omega end. Omega is simply the last carbon. So here I got 18 in a row. So it's octadecane oic acid, also known as stearic acid because it comes from fat. So this is a saturated fatty acid. There's no double bonds. Here's an unsaturated fatty acid. Okay. Again, I got 18 carbons in a row, so it'll be octadecanoic acid, but that double bond right there makes me say octadecene oic acid. Now I have to say, where do I first encounter that double bond? Here's carbon number 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's 15 octadecene oic acid. Then notice that here's the big one, here's the big one. It's cis. So it's cis 15 octadecene oic acid. So what I'll point out is that in the common nomenclature in health and nutrition, oh, omega-3 fatty acids are good, right? Well, here's the omega end. So here's omega-1, omega-2, omega-3. This is an omega-3 unsaturated fatty acid. So that's supposedly good. What if you were to put this in a vat and start frying French fries with it, okay, as an oil? Then some of that cis bond could have been converted into the trans bond because the trans is more stable. And what do we know about trans fatty acids? Well, they're bad. But is it an omega-3 fatty acid? Omega-1, 2, 3, yes it is. But it's still bad because it's trans. So when we have a second carbonyl group, we usually use oxo. The older systems used keto. So here we have 1, 2, 3, 4 in a row. It's a carboxylic acid, so butanoic acid. And the substituent on number 2 is an oxo group. Okay. So we could say also to keto. And this is also in the alpha position, isn't it? So we could say alpha keto butyric acid. So if you know about metabolism, you'll see this in metabolism of certain things. And then this one, 1, 2, 3. So propanoic acid, and on the 2 position is hydroxy group. So hydroxy propanoic acid, or in the alpha position, alpha hydroxy propionic acid. That's the old-fashioned name right there. Its common name is lactic acid. Okay. So you produce lactic acid with anaerobic metabolism in your muscles, don't you? In another chapter, we'll learn why you do that. But this is formation of this oxidation product from either bacterial or air is what makes sour milk sour. The acidity of lactic acid is what's caused milk proteins to precipitate and start to look bad. So carboxylic acids are really the kings of functional groups, and the carboxylic acid group is called carboxy when it's used as a substituent. So this is carboxyfred. Again, if we're going to name this as benzoic acid, this would be called carboxy group. But we could also just say benzene dioic acid. So any questions so far? Okay. So what about naming salts of the carboxylic acids? So you name it as the acid, but you drop the word acid and you make it end in O8. So oic becomes O8. And the common names simply use 8. So here's an ionized carboxylic acid. So they took stearic acid or octadecanoic acid and they treated it with probably sodium hydroxide. And you get sodium octadecanoate. So octadecanoic acid became octadecanoate. Common name, stearic acid becomes stearate. Okay. So this one becomes 3-hydroxybutanoic acid and then 3-hydroxybutanoate. Okay. So the physical properties of carboxylic acids, they're extremely polar. So they're often liquids or solids. They're soluble in water if there's not too many carbons, if the R group is not too big. Increasing order of solubility are ketones, aldehydes, alcohols, and then carboxylic acids. And what they found, if you put carboxylic acids in water, they often float around as dimers. Okay, so an extremely strong hydrogen bond here and here. So carboxylic acids have a pKa of about 5. They're mostly ionized at physiological pH, which is 7.4. See, I addressed that down here. Okay, again. And then fatty acids tend to precipitate in hard water. So hard water contains a lot of calcium, magnesium, iron, in other words, divalent cations, and they will precipitate soaps that are basically sodium and potassium carboxylates, like this, okay? So here is an ionic bond, right? It forms a precipitate. That's what bathtub rings are. And so the way to prevent that from happening is you use a water softener. What a water softener does is it replaces the divalent cations with usually sodium. So it's really an ion exchange resin that grabs onto the divalent cations and then releases sodium in their place. So sodium won't form these complexes with the fatty acids. And also detergents are usually sulfonic acids. So you don't have a carboxylic acid, you have a sulfonic acid, and those also won't precipitate in hard water. So that's why detergents were invented. And fatty acids spontaneously form micelles, monolayers, and bilayers in water. Okay? So, it takes a long time to draw that, otherwise I would be drawing some. But all of these would exist at the same time if I took some soap or some fatty acid, salts, and dissolved it in water. So what do I mean by a monolayer? Where if this right here were water, then notice that the carboxylic acid group is dissolving in water because of the hydrogen bonds and the strong attractive force between water. But up here would be air. Air is a nonpolar solvent, so these nonpolar portions of the fatty acids would be dissolved in the air or dissolved in themselves. And then, if I were to take this and like rub it all over my skin or something, I would be forming micelles. So water is an excellent solvent. You may have used it taking a shower before, but water isn't good at taking off oils. That's why we have soap. So what does soap do? Well, you have these monolayers, bilayers, micelles. You start rubbing it on the skin or wherever there's oils. Look what happens in here. In a micelle, this is a nonpolar region. So if I can do mechanical activity to take an oil and get it past here, past this polar part, and inside here where it's nonpolar, then I have the nonpolar inside this nonpolar portion, but the whole micelle itself is still soluble in water because of the attractive force between the ions and the water. It's really ion to dipole attractions. So the micelles, the bilayers, everything else can be washed away. And the reason why I brought up bilayer is because what does that look like to you? Maybe a cell? So phospholipids are the major components of cell membranes. Phospholipids will do these same things spontaneously. Questions so far about that? Well, we can start on the chemical properties of carboxylic acids. For one, carboxylic acids are not normally reduced in biology. Biology is an oxidative process. That's what you're doing right now. You're taking food that is less oxidized, you're breathing oxygen in, and you are oxidizing carbons. So if you just ate an aldehyde, it's going to be oxidized to a carboxylic acid. If you just ate primary alcohol, oxidized to an aldehyde, then a carboxylic acid. If you ate secondary alcohol, oxidized to a ketone. Later on, we can see that that will also be oxidized eventually with other reactions going on to a carboxylic acid. And then that carboxylic acid eventually is cleaved off by a carboxylase enzyme, and you end up as CO2 and you exhale it. So that's why we're not going to be talking about reduction of carboxylic acids. So the major thing is that carboxylic acids are weak acids. So if I put this weak acid in with a weak base like water, I get an equilibrium. And I can get an equilibrium constant. So the Ka is about on the order of 10 to the minus fifth. pKa is on about order of 5. So if you take, for example, acetic acid, pKa is 4.76. So if I made a solution made up of 50% ethanoic acid and 50% sodium acetate, I would have a pH of 4.74. So 4.74, what did I say? 7? Sorry. At pH 7.4, I got a 50-50 mixture of the protonated and unprotonated acid. What do I have to do to bring it up to physiological pH of 7.4? I have to add a base, don't I? So if I keep adding the base and I get it up to, say, that particular pH, what I essentially get is 437 to 1. What that means is that it's almost entirely in the ionized form, very rarely in the protonated form. Does that make sense? So in biology, why do we say lactate instead of lactic acid? Because it's almost all entirely in the ionized state. Why do we say pyruvate instead of pyruvic acid? Why do we say citric or citrate instead of citric acid? All because of that. So hydrogens are acidic when they have a large partial positive charge. Okay? So what I'm saying is that this right there has a large partial positive charge because that oxygen is electronegative and that oxygen over there is electronegative. So I'm pulling electrons away from that hydrogen really in that direction. So that carbonyl oxygen is making that partial charge on that hydrogen larger and more reactive. Look what happens when I put an oxo group right next to it. It becomes a much stronger acid. Don't forget, a difference in pKa of 1 unit is a factor of 10. 2 units is a factor of 100. So this is 100 times stronger acid than this one. But if I move it away a little bit, then it gets weaker again, but still stronger than this one. And so they also form salts. So here's a weak acid, here's a weak base. What's going to happen if I put these two together? There's going to be an acid-base reaction. So the hydrogen goes from here to the nitrogen, and I form this substance over here. Okay. This is a totally organic salt made by methammonium, is the cation, and 1, 2, 3, propanoate is the anion. Totally organic salt. And like amines, carboxylic acids provide another solubility switch. So the protonated form is less soluble in water, but if I ionize it, then it becomes more soluble in water. So here's something rather dramatic. The solubility of benzoic acid in water is 3.4 grams per liter, but sodium benzoate, 550 grams per liter. So this can hydrogen bond with water. This is ion to dipole attractions with water. So the next reaction, I'm really going over it simply because I want you to see how carbon dioxide is released from carboxylic acids. So decarboxylation of beta oxo, so here's alpha, here's beta. You can call that oxo or other names for it as well. Look, here I'm just gently heating it up. This thing wants to go off as carbon dioxide because it's a gas, for one, causes the reaction to be pulled that way. And also, this is not acidic anymore. This is acidic. So because of acids being more reactive, by going in this direction, you get a less reactive product, and one of the products is a gas which leaves where the reaction is taking place, drawing the reaction in that direction. But the point I wanted to make is like, oh, you don't need an enzyme, just gentle heat can do that. So I can emphasize here that chemical reactions in biology, for the most part, will happen anyway, even without an enzyme. The enzyme is just a catalyst. It doesn't make something go that isn't going to go. It just makes something go faster. So finally, today we'll look at this last reaction, esterification, or Fischer condensation, or Fischer esterification, whatever you want to call it, after Emil Fischer, a very famous chemist. So esterification is the condensation between a carboxylic acid and an alcohol. Oops. To form an ether. Here you can see the problem with, right in your own textbook. Okay. So here's what happens. What we know about carboxylic acids is they like to lose whatever this is, this hydroxy group right here. So if I bring in an alcohol, a couple of things I notice. Carboxylic acids like to change whatever it has on here. And then we also like to form water a lot. So here we got a win-win. I form water. Now the carbonyl carbon needs another bond. That oxygen needs another bond. So I just let them have it. And this is an ester. So the carbonyl to the oxygen to a carbon is an ester. Here's the name that we'll look at in a few minutes, or actually tomorrow. And because these are so readily reversible, I put them in the same reaction. Here's esterification, and here's, oh no, I didn't do that. Oh, I just added them in different order, that's all. So again, carboxylic acids like to change whatever is on there. And can it make water? Yes, it can in this case. So that carbonyl carbon needs another bond. That oxygen needs another bond. So I just give it to them. And what you'll see is that the first name comes from the alcohol that you used, right? And the second name comes from the acid that you used. So anyway, we'll just stop there. Anybody have any questions at all? Seems like a lot of material.
Yeah, that was a lot of material. Maybe tomorrow I'll have questions.
You're gonna spend the rest of the day recovering. So I always call this baby organic, and so students who have taken organic chemistry, guaranteed they have been traumatized by organic chemistry. So hopefully this serves to untraumatize them. The students who have never had any organic, yes, it does traumatize them. Sorry to say. Okay, so tomorrow I don't have my normal meeting because there's a big, huge Board of Regents meeting tomorrow, very controversial one. So we're not going to have our normal meeting. So we can have our lecture at noon again. Okay, and I'll send that out as an announcement. So if you don't have any more questions, I'll just see you tomorrow at noon. If you have questions, you can always email me. So you guys have a great day, okay?
Thank you, you too.
Okay, take care.